Okay. I believe that all of you can hear my voice. Okay, so let us continue with the following section. Okay, before that, just ask you whether you can hear my voice.
Yeah, I can.
Okay, thank you. So I have shown it to you about the how to get the stationary point and then find the optimal solution for the y hat here. Okay, in k equal 2, and then this one will be the general case. Okay, just applying the formula here, then you can get your stationary point as well as you can get the fitted points at the certain level of where they happen at the stationary point. Okay, so now we will know what is the nature of our graph. So this one is one of the example for with the maximum. Okay, because you have a quadratic effect, the quadratic curvature here, then this one is a response surface. Okay, but of course, if you're looking at this graph, you want to draw it yourself, I think it's impossible. Okay, even though the control point of here, also we are not going to draw it ourselves. Okay, unless you have the software, then you can draw it out. Okay, but the idea is if you have a response surface, this one will illustrate for you is a maximum point. Okay, for this one will be illustrate for you is a minimum curve, where you have a minimum happen at here. This one is a maximum happen at this particular point here. So this point is identified by the software itself. Okay, so you have a minimum point, you have a maximum point here. Okay. If you want to draw it in the diagram here, so this one is for the case of minimum, and then you have another one is where you do not have a maximum or the minimum here. So that one is called the shader point here. So the shader point will be happen if you draw the plane will be have this style of the shape here. But of course, as I mentioned again, we are not going to draw the following graph. Okay, so this one is just an illustrate for you how is it the response surface look like after you get the equation. Now, how are we going to find out the optimal solution? So to get the optimal solution, the characteristic of the response surface, we try to categorize it using the following idea. The most straightforward way to do this is examining the contour point of the fitted model. But unfortunately, we are not going to draw this out the contour point. Okay, if there are only 2 or 3 variables, the construction and integration of this is relatively easy. Okay, because if you only have 2 variables, 3 variables, then maybe it's possible. But if you have many variables, then how are you going to draw the control point with the 4 dimension, 5 dimension? Okay, so that one may be a bit difficult. So, but we will use the formal way of the canonical analysis, where we can do the analysis of how to identify what is the stationary point here. Okay, so how we want to do it using this analysis is actually we transform it, as you can see from this diagram here. Before that, the direction is a x1 and the x2 in the following x-axis and y-axis. So the analysis is try to transform the axis of the x1 and x3, x1 and x2 to the new axis is called the w1 and the w2. Where your control point will be that they will have a following one. They try to transform it to the new variable here. So it's helpful. First, this one is wrong. No w here. Is to transform the model into the new coordinate system with the origin at the stationary point. Okay, so before that, for this one x1 and x2, the origin is not in the stationary point. The origin is at the here 0, 0 here at this point here. Okay, so but we try to transform it such that the origin to the new coordinate system with the origin at the stationary point here. So this one is the stationary point. So we try to transform to this direction is a w1 and w2. and then rotate the axis of the system until they are parallel to the principal axis of the fitted response surface. So they do it, rotate it out in the following one. So how they rotate, we don't need to know how they rotate it. The important thing is we need to know how to find the optimal solution. So this one is the idea of the coequation here. So the resulting fitted model will be have a following form, where the fitted model will equal to the fitted for the stationary point plus the lambda I multiplied by the I squared. So after you transform, it's no longer x1, x2 anymore. It's actually is a w1 and w2. If you have only x1, x2, if you have x1, x2, x3, then they become the I is equal to 1 until the 3, or in general until the k. Okay. So the wi is actually the transform independent variables, or we call as a canonical variables, and the lambda I here is the constant. Okay, so the lambda I here actually also is called the eigenvalues of the metric B. Okay, the eigenvalues or the characteristic roots of the metric B. So therefore, we need to know what is our metric B just now we obtained. And then from the metric B, we calculate out the eigenvalue for this thing, for the lambda I here. So the metric B, just now I have shown it to you, the metric B will given by here. The metric B will be diagonal is your quadratic effect, the off diagonal is all the iteration. Then because this is a symmetrical matrix, so the upper triangle and the lower triangle, they are the same. The diagonal is your quadratic effect. Okay. So to characteristic it out, here I have shown it to you here. The nature of the stationary point is determined from the sign of the eigenvalue of the metric B. So if all the lambda 1 until the lambda k are all negative, then the stationary point is a point of the maximum response. If your lambda 1 until lambda k are all positive, then the stationary point is minimum response. Otherwise, this one is called the shader point here. Okay, so if you have a mixture of the positive and negative sign, then this one is the third one. Okay, so our objective is want to get out what is the nature for the stationary point. So by finding the lambda 1 until the lambda k. So the lambda 1 until the lambda k is actually the eigenvalue of the metric B. So this one is the way how we want to get it out the stationary the nature of the stationary point. Okay, so let us go through for the following example here. So in this example, because we want to fit the quadratic, effects. So therefore, we need to have a more points here. Okay, if you recall back what you have in the previous one, in the last part of the in the last a few slides of the first. The part one lecture notes, I have mentioned to you that if we want to fit in the quadratic effects, just now I have repeated it. If we want to fit it, then we want to fit in the quadratic here. We need the number of nano-parameters is 6. So therefore, if we based on the factorial point, a number of center point may not be enough. So therefore, we need to run out the additional point is all the option run. So here will be showing to you what is the option run here. So in this experiment here, in this following experiment here, we have 3 different response. So we want to study the 3 different response of this variable here. So of course, we can have a response for the first one. Okay, we have a response for the first one is the yield. The response for the second one is the velocity. And then the third one, the response for the third one will be the another one. Okay, so there are 3 different response up here. So in the following analysis here, we have a x1 and x2 are the 2 important factors we consider here. Okay, where the first variable is the x1, the second variable will be the x2 here. Okay. So in this following example here, you can observe it. This one is normally what you have studied before. This one is a number of factorial point is equal to 4, because in this case we are studying is a 2 power of 2 factorial design. So therefore we have a 4 of them, and for the factorial, and then because the factorial point is the natural value is 80 to 90, so 85 is a middle, 170 to 180, so the middle is 175. So these are the parts of the number of the center will be equal to 5. Okay, so you also have additional, another one is called the auxiliary here. Okay, the auxiliary will be given by these 4 values here. Okay, so how to get these 4 values? Of course, we cannot get directly from this one. Actually, what we get is from the quoted variable first. So the number of factorial point is 4. We have a quoted is -1 and +1. For the center point, we put the 0. For the auxiliary here is actually, once we get the relationship of the x1 and x1 and xi1 and x2 and the xi2, that's now what we have obtained, then the auxiliary will be equal to the here is 1.414. So this one is actually equal to the square root of the 2. This one is the negative square root of the 2. This one is a square root of the 2. This one is a negative square root of 2. So I will explain to you why is a 2 here. The 2 here is actually referred to the k. The k is equal to 2. Later on, at the end of this part, you can see that this value is actually the square root of the k here. Okay, so from the 1.414, you can convert it back. Then you will get is 92.07. Okay, then after that you have a 0 here is still 175. Then if you have a negative here, you will get is 77.93. Of course, you want to get this thing, then you need to find the relationship of the x1 and with the xi1. Just now I have shown it to you. If you want to repeat again, x1 is equal to xi1 minus away the average value is 80 plus 90 divided 2 is equal to 85, divided by the bottom will be the difference here divided 2. This one is a 10 divided 2, you get 5. Okay, so you have a x1 in term here. Another one, x2, also you have a xi2 is minus by the average value is a 175 divided by here 10 divided 5 is 5. Okay, so now you substitute the 1.412 for 1.414 here, 1.414 here. So you rewrite out, you'll get your xi1 is equal to 92.07. So if you put the negative, then you get 77.93. Okay, so this one is an additional point. If you wish to form the quadratic equation, okay, where we call I also call the name as what they call as a central composite design. It's called CCD. Okay, before that I also have introduced to you the name itself. It's called the central composite design, where you have an additional of the auxiliary. So because this one is a 2 by 2, you have an additional is a 4. If you study for the three factors, x1, x2, x3, they consist of the 3 factors, then the auxiliary should be 6 of them. Okay, so in this case, you only study for 2 power 2 factorial design, so therefore the auxiliary is just a 4 points only. So these are the additional points. You run the experiment, then you have the following result is given by here. Okay, so this one is the experiment where you run it out. From the here, this one is what the diagram is showing to you. This one is show the factorial point. For factorial point, this one minus become the 1. This one is a 1 a. This one is 1 minus 1 is a a. This one is a ab. This one is a b. Okay, if you go back to the previous one, so this one of course is a center point. then the also run here. 1, 2, 3, 4. Means that all the in this experiment you need to run how many possible here. You have a single replicate. You have 1, 2, 3, 4, and then you have a run 4 of there. Is all together 8 experiment you need to run at the same time. In the center point, you also need to run. In this case, you run for the 4 different. You run for the 4. Okay, you run for the 4 different. 1, 2, 3, 4, 5. You have a run the 5 of them. So altogether is a 5, 4, 4 is a 13 experiment you need to run so that you can get the yield for first one or the velocity and the molecular weight. So these are the experiments you run in. Okay, so we just concentrate on the first one first. Okay, because the rest of them are repeated. So if based on this one is your response, then whether this one is whether if you fit for the quadratic equation. So this one is it they get the optimal is a maximum or the minimum solution. Okay, so this one is a diagram we have. If we plot the contour plot, this one is a contour plot we have. Okay, so it's show you that the curve is a maximum curve. Okay, or the response surface is maximum. So we will expect we get the optimal solution. Okay, this one is the first variable time. This one is a temperature. So if the maximum is happen at here, so you need to know what is the temperature at what level of the temperature, and then what level of the here the time is lead you to the maximum solution. So that one we can find the stationary point. Okay. So basically, we can be roughly will guess here the optimal solution. If you see the plot here, roughly here around 80 plus. This one, if the optimal is here, this one is happen at the 100 plus. Okay, it's somewhere around here. Okay, from the plot itself. So now we are looking at the optimal solution and then to get out the equation out. Okay, so first thing is you need to know what is your B here. Okay, the B here will be given by the beta naught and beta 1 here. Okay, the B here, the B will be equal to beta 1 hat and the beta 2 hat. So from the effect itself, you can calculate this one is the beta naught and the beta 1 hat. And then the B here is equal to the quadratic effect here. Maybe I use. This one is a B here. This one is a B, capital B you have. Okay, B11, you B11 is given by here. The B22 will given by here. Okay, and then here is a B12, B12 hat is this one, and the B12 hat is this one. Of course, how are you going to get your B12 hat? Because you already run the factorial, you already have a following data set. Then you can be use a regression idea to calculate out what is your all the parameter estimates for the regression. Okay, so you can try it out. Then you can get out what is a B1 and BB22 here. So once we have it, we just put it here. This one and this one. Okay, you have these two. Okay, so just now I have shown it to you the formula for you to get the optimal solution or the stationary point will equal to minus half multiplied by B, capital B inverse B. Then you multiply, you will get your this one is a stationary point. But bear in mind that this SS is a refer to the coded variable. You code the variable is only for the coded variable. So the 0.389 and the 0.306 is not the real variable. So it's a coded variable. Then of course we can be apply the here the x1 will equal to the z1 minus 85 divided by 5. So you by substituting the 0.389 you will get it, the xi1 will equal to the 86.95. You will get your the natural variable over here. Similarly, for the second one, you have x2 will be equal to the xi2 minus 175 divided by 5. So you substitute it with the point here 0.306. So you get the 2 will equal to the what you have is a 176.953. Okay, so this one is referred to the minute. This one is referred to the Fahrenheit. So if you observe, this one is 86.95 and the 176.53. This one is just now, if you can be able to plot here is roughly around 87, and then this one is they are really around the 176. Okay, because we not necessarily know the optimum mass we had exactly here, and then how we want to read, but roughly we know it here. Okay, so this one is what you have. This one. Okay, so this one is just a stationary point. To study the nature of the point itself, of course, we need to calculate out the eigenvalue. So how we want to calculate eigenvalue? Okay, the eigenvalue given by, or the eigenvalue don't want to given by first. Okay, are obtained by using the finding the eigenvalue. So how to find the eigenvalue? It's just the determinant of the B minus the lambda multiplied by identity matrix will equal to 0. So the B here, just now you have the B. The B here will be get it from here. The B is actually what you have is a B here. Okay, so I just copy down the value here. Minus 1.376. Then the second position is 0.125. 0.125. This one is minus 1.001 minus a lambda 1001 equal to 0. Okay, you no need to you just follow the how to find the eigenvalue. I think it's this one is just a way. Okay, so from here, of course, you find the determinant. This one is equal to negative 1.376 minus by lambda. The second one will be 0.125. The third one will be 0.125. The following one is okay. So this one is not the absolute value, it's a determinant. So the determinant is just the cross product of here. Because this one is a 2 by 2. Okay, the cross product if the determinant is here equal to 0. So this one is just a quadratic equation. It's a quadratic equation. So therefore you get, if you expand the square. Okay, so you solve the quadratic equation. I believe that you can use any of the software. If you have calculator, you just use the calculator. Then you can find out your lambda 1 will equal to negative 0.9634. and the lambda 2 will equal to the negative 1.414. Okay, so this one 4141. Okay, so these two, both of them is negative. Okay, both of them is negative. So therefore, you obtain the answer should be the maximum. Okay, the optimal is maximum. So this one is what you have here is mentioned to you. If the both of the lambda is now negative, then the stationary point is maximum. This one can be confirmed from your control plot. If you're able to draw it out using the software, then you can get the maximum. If you cannot get it out, you cannot illustrate it here, then of course we need to do the calculation, okay, to identify whether this point is a maximum or the minimum point. Okay, so actually this one is the maximum point. Actually this one is not the maximum point. The maximum point is referred to the optimal solution here. So this one is the maximum the problem. Okay, so the stationary point you obtain should be the maximum. Okay, so this one is what you have in your following example, this example where you have how to calculate out your equation is given by here. Okay, so this one is let me see. Yeah, the explanation, if you can't see my wording, actually I will explain it here. Okay, so this one will be what you have, the form of here, and then you get the equation out, you get the lambda is equal to here. Okay, then this one is a maximum. Of course, we are not going to go through it, the W1 and W2. Okay, because this one is the W1 and W2 is after they have transformed. What we are interested is actually on this part. What we are interested about the y hat. Okay, in terms of the y hat, in terms of those of the stationary point. Okay, we are interested about the y hat here. What is the optimal solution for this particular values? Okay, if you observe it, the point here, this one is you see the control port is from 74, 76, 77, 78, 80, 80. Then around here, maybe you substitute. Once you get your stationary point, you can substitute it. You can get your fitted value. So the fitted value maybe optimal is around what is the value here. Okay. So the optimal value you can just substitute inside. Both from here, just now we have calculated out the optimal value will be equal to 80.21. Okay, this one is for your y hat. Okay. Then this one is just a general statement. Okay, for the experimental with the fitted of the response surface. Okay, so all these steps is actually I have mentioned it to you. We need to have enough information or enough data point to run our experiment, and then of course we can check how good is the model fit based on just now the first example. I checked for the iteration effects. Okay, and then I also check for the quadratic effects. Okay, so these are some examples or some feature of the response surface where you want to form your equation. Of course, in your experiment, sometimes you also in your analysis of variance or 2 power k factorial design, you also involve the blocks. So if you have a blocks, then you need to perform in the block forms. Okay, and then if you not deal with only single replicate, then of course you need to estimate the error. Okay, once you have an error, then you can test the significance of all the parameters. Then from the parameters, then we can form the equation. You can estimate your model coefficient, same like this one. You can estimate your parameter the equation of all these things. The parameter of the beta 1 hat, beta 2 hat, beta 1, beta 2. This one is what they mentioned. Okay. And then, of course, we can predict the variance throughout the experimental under the certain region. Then this one is, of course, this one we are not deal with it for our course here. If they consist of outliers, then is it your formula will be suitable for those of you who study the regression model, then you also know how to checking the outliers, and then you may deal with the missing values. Okay. So these are some examples only, may not be the fixed one. I just get it out, just let you know about in the response surface. Okay. So the following one, the following or the last slide here is about the just now why we have the square root of the k here. Okay, so I'll just illustrate for you what is called the second order model. So I just use the same example here. Okay, so this one is for the case of the two power of a 2 factorial design. This one is a 2 power of 3. This one is a 2 power of 2. This one is a 2 power of 3 factors. This one is a 2 factors. Okay, so basically, if you want to run the CCD, the center composite design, you need to have a number of factorial. The factorial run, of course, is needed, and then the number of center run is at here. Then, of course, you need to run some more. That one is called the star run or the auxiliary run. So the auxiliary run will be equal to the 2 times the k. So because in this case, the k is equal to 2. So therefore, in this diagram, you have the 2 times the k will equal to the 4. So the 4 run will be here, 2, 3, 4. So if you study is a k equal to 3, from the diagram here, you know that they consist of the 6 surface. So therefore, you run the auxiliary run is equal to 2 times the k is equal to 6. So where is the 6? 1, 2, 3, 4, 5, 6. So these are the auxiliary runs you need to run it out if you want to form the equation or form the model for the CCD. Okay, so if you observe it out, this point is from 0 to alpha. Okay, this point is just a 0 to alpha. Okay, so what is the alpha here? The alpha, I will explain it here. The CCD is very efficient design for fitting the second order model. There are 2 parameters in the design that must be specified. The first one is the alpha distance. So the alpha, where is it called the alpha of the auxiliary run from the design center, and the number of the center point. So not basically the number of center point they suggest is just 3 to 5 points, because you need the center point for you to estimate the errors. Okay. So the alpha here, we can select the alpha based on the following criteria, where here the required model have a reasonable consistent and stable variant of the predicted response at the point of the interest x. So we want to have a stable of the variant. So how we want to have a stable of variant? So the center composite design, or they call as a CCD, is made the rotatable by the choice of the alpha. So what is the alpha here? The alpha will equal to the here is this thing is power of 1 over 4. Okay. Okay, wait, okay, the alpha is equal to the first one is equal to the NF is equal to 1 over 4 here, or equal to the, okay, so in this one, there are a few of the criteria to decide for the alpha here. So one of the alpha, the first one can be considered as a alpha is equal to the NF power of 1 over 4. This one is the first version. Okay, so you have another of the alpha. Okay, I will write it down here. You have another one. It's called the Spherical Ccd. Okay, another version of the CCD where they can have here. They will set the alpha square root of the k. Okay, there are 2 different criteria of here. The first one is, of course, if they want to have a stable variant, then they will choose the alpha is equal to the NF power of 1/4, then the alpha is a point where they consider. Okay, because once you get your alpha, then you will know what is the point you're going to run. You are not running of the point here, you are running here. You're running your experiment at this particular. Once you know it's a square root 2 here, then you need to convert to the following natural variable. Then you only run your experiment under this condition, then you get the following results. Okay, so the first thing is you need to know what is the oscillon, where is the position for oscillon is run. In this case, it's a square root 2. So they were based on there are many criteria. If you have a textbook, there are many criteria. Okay, I just show you two of them. One of them is using the following criteria. The second one is they said the alpha will be equal to the square root of the k. So this one is what you have seen in the example above. They are using the alpha equal to square root of k. So the k for the above case is k equal to 2. Therefore, square root of the k 2 is equal to 1.4. Okay. So of course they still have other criteria where we can be considered to find out the what oscillon. Okay. So this one will be the last part for the response surface methodology. Okay. So when you go back, you can try out how to fit the regression equation for this one, so that you can get your beta 11 and beta 22. You can try it out first. Okay. Then I will give you the tutorial question, because under this chapter tutorial question will be not very long. The important thing is you know how to find the center, all this CCD, and then how to find the method of the Stegner action and the method of the Stegner division. Okay, so this one is for the lecture class today. In fact, in your tutorial, because some of them asking me the question, I have a great here. No, this one I have. Okay, if maybe it's not here. Let me see. Okay. Okay. I will share with you. Hold on.